Today's lecture is mostly a continuation of what we were doing in the last one. That's when we discussed about the linear neuron models, considering the linear activation units. And today we are going to continue mostly with that, but more stress on the gradient descent algorithm. And later on in the class today, we'll try to introduce the nonlinear activation units. So, although it depends on how much of progress we make today, okay, about these two topics, but we'll try to cover both these things in this particular lecture. If anything is a spillover, that will continue in the next one. Now, what I want to say is that in the last lecture, we had actually presented the case of a linear neural model, where essentially the interpretation that we had tried to focus upon is that, as if to say that given a set of data, okay, supposing you have got essentially a function, let's say a function y, okay, supposing an output y, which is function of some variable x, a simple y is equal to fx type of a function, where we had certain set of observations, okay, maybe that these are the set of observations that we had got, okay, and then essentially the problem was to fit a straight line through this data, okay, and it is essentially that fitting of the straight line which we had modeled using the linear neuron. So what we essentially had was that we had a single neuron which worked on the linear activation unit, okay. Linear activation unit means essentially it was having Vk is equal to summation of Wkj xj, okay, and where j is equal to 1 to n. Now, for a simple case, we had only one such x, let's say x1, and we had the bias which was b, okay, or we called it as x0, and then we got the output, and this could be extendable to the multidimensional case. Now, one thing which we need to interpret is that, as long as it's a single variable, okay, like y is a function of x, we know that it's a line fitting, and essentially we have to tune the two parameters, that's the slope and the intercept, these two parameters only, right. So, essentially it is a two-dimensional fitting problem when the variable is 1. That means to say that in this axis we had x, and in this axis we had y, and we had assumed that the function is going to be y is equal to fx, and it's a linear function. That's what we considered, okay. The function could be non-linear as well, okay, but that case we are considering later on. Now, what's important to think of is that the extension of this idea, that if instead of a single variable x, okay, supposing y is dependent upon several variables. Let's say that y is a function of, just to make the problem a little more complex, we make it f of x1, x2. So, it's dependent on two variables. So, in that case, the line fitting problem that we are looking at it, okay, is essentially becoming a three-dimensional line fitting problem, okay, in the sense that in that case, we can consider that we have got two axes like this. Let's say this one is our x1 axis, and this one is our x2 axis, and this is where we are plotting the function, that's to say y, okay. So, y is a function of x1, x2, so which means to say that essentially in the 3D we will be getting some points, okay, which will be obtained to us, which will be given to us from the experiments that we perform, or rather the training that we impart to this network. And essentially it's a problem of fitting a 3D straight line, okay. So, and how is it getting modeled into the neural network? Simply we will be having a neuron with two inputs x1 and x2, okay, and the third adjustment will come from the bias. So essentially we will have three synaptic weights to tune, okay. If this is our neuron K, in that case it will be WK1, this one will be WK2, and this one will be the bias, that is WK0, okay, and finally it will be the output. Now how to interpret the fitment of a 3D straight line, okay. Essentially if you look at a 3D straight line, this has got three components, okay. It has got slopes, okay. In fact, I mean, it has got a single 3D slope, you can imagine, but that 3D slope, that we can resolve into two components. One component of that slope is along the x1 y plane, okay, and the other component is along the x2 y plane. So essentially we will be having two such projections, okay. Let's say that in the x1 y plane, the projection of the fitted 3D straight line is going to be, let us say, WK1, and the projection of the 3D straight line onto the yx2 plane is going to be WK2. So essentially again we are having these two parameters WK1 and WK2 to be tuned. So although it is a 3D straight line fitting, okay, we are essentially breaking it up into the fitment of two slopes. One is WK1, which is the slope component along the x1 y plane, and the other is the component of the slope along the x2 y plane, okay, which is WK2, okay, and on top of it we have got the bias also added to it. So essentially it is just tuning of three such parameters. If we tune those three parameters, we can fit a 3D straight line, okay. Now up to 3D we can bring into our visualization, but anything more than 3D we cannot bring in into our visualization. So we have to build up this concept. So what I would like to point out is that if in that case we take a function y is equal to f of x1, x2 up to, let's say, xn, that means to say that making the variable itself n-dimensional, in that case the neuron model will be looking like this, where we will be getting the inputs from x1, x2, x3 and so on up to xn, okay, and this will have their respective adjustment parameters wk1, wk2, wk3, etc. up to wkn, okay, and then on top of it we are also having the bias, which we can imagine that a bias of, let's say, +1, and then we have here WK0, okay, where WK0 will indicate the weight, which essentially stands for the bias itself. I mean, just giving it a fixed input of +1, and then the output, which will be simply the y is equal to summation form, I mean a linear summation form WKJ xj. Now in this case the interpretation is like this, that we have fitted an n-dimensional straight line, and essentially that n-dimensional straight line is having so many gradients along x1 y plane, gradient along x2 y plane, gradient along x3 y plane, and so on, okay. I mean it can be rather projected into all these n different hyperplanes, and then these will be their individual slopes, okay, and then we have the bias. So this parameters, if we adjust combinedly, then it is the problem of fitting an n-dimensional straight line. Now n-dimensional straight line we can't bring into our visualization process, but I mean we can certainly build up this concept just by extending our thoughts from what we have already learned for y is equal to fx and y is equal to f of x1, x2, okay, just extending that part. So this is the interpretation that you can keep in mind, okay, and then the problem we had looked at it this way, that we were defining the error that we are doing in the process of fitment. So the problem was simply decided like this, that for this y is equal to fx function, let us say we had fitted a straight line, and then we had a number of observations, okay, where naturally the fitted straight line is not exactly passing through all the observations that we had made. The fitted straight line indeed made some errors, okay. Some error values are positive, some error values are negative, but in order to make a combined estimate of the error, we simply made the square of those errors and we just added it up so that we get a combined error, okay, over all the points through which we are fitting this, okay. So that was the combined error measure that we had defined, okay. And if we have the error, in this case it is the error which we could plot as a function of two variables, W1 and W0, where W1 is the slope and W2 happens to be the intercept, okay. And then we had considered a 3D surface, okay, through which we could imagine that if we place anything on a 3D surface, okay, let's just place an object, and then its natural tendency will be to come to the point of local minima. Now, there was a question that can come into our mind, okay, very easily, that is there any guarantee that it will really have such a kind of a minima, and if at all, if it has got a minima, is that minima, I mean, how confident we are that it will be a global minima only, because ultimately what our objective is? Our objective is to fit a curve, in this case a line of course, but our objective is to fit a curve, okay, which is actually giving the minimum error, isn't it? That's the position that we are looking for. We are searching all over the place for the best combination of W1 and W0. That's it, okay. And for an n-dimensional problem, we are finding out the best combination of W1 to Wn and the bias, okay, so that the best type of fitment is there, okay. What is the best fitment? Minimum error. But what is the guarantee and what is that minimum? Now, likewise, we could imagine, I mean, our imagination can work only up to a three-dimensional surface, as we had said that if we plot the error, okay, and if we have the two parameters to be adjusted, let's say W0 and let's say W1, okay, and we had a surface of this nature, okay, where we were placing some object, okay, and this is a 3D surface that we had considered, and this object was, I mean, if its initial position is here, then we want the object finally to be here, and for the object to come and rest over here, okay, whatever the corresponding positions of W0 and W1 are, okay, that is the solution. So this is the error that we have plotted. So it's a 3D surface, but again, when we are extending the problem so that we have to adjust W0, W1 up to Wn, all these n parameters simultaneously, then the problem is extended to an n-dimensional error surface, okay. It's essentially an n-dimensional error surface that we are looking for, and there we have to find out that what the minimum is. Now, look at the way whereby I have drawn this diagram, okay. I have drawn this diagram in a very simple way, in the sense that we can clearly see from this object that this particular surface has got only one minimum, okay, only a unique position of minimum, and that is where it is going to be, okay. But I mean, it's not guaranteed that a surface will have only one minima. I mean, just try to imagine it like this, that supposing, okay, let's hypothetically imagine that the surface has got a shape like this, a 3D surface only, but it has got a shape like this, okay, and it has got a minima, it has got another minima, okay. Now, these two minima may be different in their magnitudes, okay. I mean, out of the several minimas which a surface can exhibit, okay, only one of the surfaces, I mean only one of such positions will be the global minima, where the actual minima exists, okay, and all other places will be having, all other minimas that we consider around it, they are all the local minimas. So there is a possibility that if you start with some initial state, okay, supposing the initial state is here, the initial state could be there also, okay, and we allow the system to adapt. That is what it is doing, isn't it? It is ultimately adapting itself, okay, learning and correcting itself so that it gets the best fitment. So, while doing that, in doing that process, it could either come to the absolute global minima, I mean that is what we want, or it could come to one of the local minimas and get trapped into the local minimas. So, really speaking, it is very much problem dependent, okay. I mean it depends on the problem, and also it depends upon certain neural network configurations, okay. So, right now at this stage, I mean let us keep this aspect open, okay. Let us not immediately come to the conclusion that any neural network and any problem that we consider is going to have a global minima only. I mean it may not be. I mean let us take it that way, that it may not always guarantee a global minima, it could be a local minima also, and that is what we have to keep in mind, okay. But okay, if there is a global minima solution, ultimately we have to reach for a global minima, okay, and how we reach it, okay, that is what something that we have to think of. Now, once again we take the same problem in the sense that we have got these kind of a surface, right, and we have kept some initial position and the object happens to roll down, okay, to this. Now, how is it rolling down? It is following the direction of the gradient, rather the gradient is pointing up, okay, and the ball or the roller that is coming down. So, it is against the gradient, against the, I mean opposite to the direction of the gradient where it is moving. So, this is what we call as the gradient descent, and we are going to consider the gradient descent algorithm. So, let us look at the gradient descent algorithm, what it means. Okay. Now, let us consider that we have got p number of points. P number of points means we have p number of observations, okay, observations for which the data is already available. I mean observations which we are using for the actual training of the network, right. So, our combined error measure, if E is the combined error, okay, then E can be written as the summation of EP, right. So, it is summation of EP over P, and I have been indicating this P as a superscript, okay, indicating that it is the error for the point P. So, it is the combined error that we are considering, and if we consider the every individual error EP, that can be defined as a what? As the summation of the square difference. So, what we can do is that this EP, that is going to be T0, but T0 happens to be the target, okay, minus Y0. So, that is for the point P. So, T0P minus Y0P, okay, whole square, okay. If this is the output, I mean this is the target output and this is the output that we have got from the system. So, it is what is desired. So, this is the desired and this is what we had got as actual, and there is indeed a departure between the desired and the actual, and this is for one output unit. But mind you, typically a neural network is not going to have a single output, it is going to have several outputs. If we have, I mean like say for example, you imagine any decent control system, okay, any typical control system that you can imagine for any industrial application, that is certainly going to have multiple parameters to ultimately control, isn't it? I mean it has got several outputs to control. So, we can indeed pose a problem like this, that we are going to have several such outputs, okay, like y0, y1, y2, etc., okay, up to, let's say, ym, and each of these are going to be a function of x1, x2 up to xn. Okay, y1 also is going to be the same. So all these, there are different outputs. So what we have to do is that in order to measure this combined error for these, for a point P, okay, we have to find out that for this point P, what is the combined error, okay, from all the outputs. Okay, so I should sum it up over all outputs, that is where O stands for the index of the output, and this is T0P minus Y0P square. In fact, for our convenience, okay, we are not exactly taking it this way, we are just multiplying it by another factor half, okay, and this is only for a computational convenience, because the reason why I tell you is that ultimately we are going to find out the gradient of the error, right, and this being a squared quantity, okay, the gradient is naturally going to be 2 times of this. So having a half outside is always convenient, so that the, I mean, you get half multiplied by 2 and you get that part eliminated. So that's why it is only for the mathematical convenience that we I mean, define the EP to be half of this summation of this squared quantity. So that given this, so I mean, I hope that the things are clear. The summation over P is the number of points, okay, over which we are observing, and O is the number of outputs, number of different output units that is existing in our neural network system. Yes, please. Is there any doubt that when there is only one function? No, there is not one function. In fact, I mean, that's I mean, good thing to point out. What we have to consider is that y0 is a function f1 of these, y1 is a function f2 of this. Okay, so again x1, x2, like this up to xn. This is or I mean, just to put it in a consistent manner, y1 is f1, y2 is f2, y3 is f3, and ym is fm. So essentially it's all different functions. I mean, if we have m different outputs, then we are going to ultimately approximate m different functions. Is it clear? Yeah, yeah. So it's a combined function, you know. I mean, ultimately we are ultimately our objective is to generate m outputs.
So why would an output have a network of m outputs when the set of inputs is same?
Yeah. So I mean, the input parameters could be common. Okay. The input parameters to it could be common, and then it could have a number of observations obtained out of it. I mean, it could be having number of conclusions drawn out of it. Like, so for example, I give you a simple example. Okay. Let us say that the input is a satellite image. Satellite image means what? That we have got several such inputs. What are the inputs? Those are the pixels, right? Now, these are the inputs to the system, and then ultimately we are wanting a classification to be done. That means to say that which areas are the vegetation areas, okay, which are the water areas, okay, and like this we may be classifying the satellite image into 3 different classes. But mind you, this classification will be based upon all the pixels that you are receiving. So if you are looking at the classification number 1, the classification number 1 is a function of, is some function of all these pixels. Classification number 2, that's also a function of all these things. Classification number m, that's also a function of all these things. Okay, different functions. So ultimately this is our network, that we will be having m different inputs, m different outputs. Okay, this n and m could be anything. Okay, so we are looking at the problem that way. Okay, any other doubts? Okay, if there is none, I can continue. But okay, so this is the definition of the error. that we are considering, right. So, now we have to do what? We have to compute the gradient of this error, correct. So, what is the gradient? The gradient we can define as follows, that the gradient we call as G. G will be defined as del E del Wij. Okay. So, what is Wij? Wij is nothing but the synaptic interconnection weight, okay, between what? From neural J to neuron I. Okay. So, if we make it like this, in that case, this problem, I mean this dou E dou Wij, okay. Now, out of this, E becomes the summation of this EP, correct. And what we can simply write is that this is dou Ij of summation of EP, okay, over this P. I mean that's just a different way of writing this E, right. And this effectively is nothing but, I mean we can take this under the, I mean we can take this summation under this. So, this is dou EP dou Wij, okay. So, this is the gradient, I mean we have to find out the gradient of error for one point, okay, with respect to one set of weights, okay. So, Wij is only one set of weights and there are several such weights in the system, there are several synaptic weights in the system. So, it is the gradient with respect to this particular weight of Wij that we are considering, okay. And in order to consider that, we have to sum it up over all the observations P, okay. So, this is summation over P for dou EP dou Wij, okay. Now, what we have to simply do is to perform this differentiation, and to perform this differentiation we just apply the chain rule of differentiation to compute this. So, what we do is that we have to compute ultimately this thing, isn't it. So, to compute this we simply define dou E dou Woi, let us say, okay, and that should be equal to dou E dou Y, okay, into dou Y, oh okay, let us say dou Y0, okay, where Y0 is, I mean just to recollect, Y0 is the output, okay. So, this is a derivative of E with respect to the output, okay, multiplied by dou Y0 dou Woi. Is that right? I mean this is just by applying the chain rule of differentiation, okay. And let us have a look at this expression. Now, this we can call as the equation number 1. So, now if we have a look at the equation number 1 and we take the derivative of this, okay, what do we get? I mean we can take the derivative of this with respect to Y0, can't we, because it is a function of, I mean this here EP has been clearly expressed as a function of Y0, okay. So, we can indeed take the differentiation, and if we do that, that means to say that if we take the derivative of 1, so we can write that from 1 what we obtain? We obtain dou E dou Y0, and that is equal to minus T0 minus Y0, okay. Is it right? Okay. This is what we are getting, right. This is for any point P that we can take. So, here I mean because it is to the power 2 over here, and because this is with a minus sign, okay, that is why half gets cancelled with 2. So, now you can realize the advantage of having a half outside it. So, that this looks pretty good, that it is dou E dou Y0 simply becomes equal to minus of T0 minus Y0, okay. So, that is the ultimate derivative that we have got, but that is the derivative with respect to Y0 only. but ultimately we want to find out the derivative with respect to WOI. So, what I have to do is simply, also to calculate this. How would I calculate this? Dou y0, dou WOI. How do I calculate this? Is it easy? Difficult? Which one? Which one do I apply? Which particular equation do I take? Exactly. I simply take the summation equation, because this one is already defined with us that y0 is equal to summation of WOJ yj, okay, and we are summing it over j. No, that is xj. Yeah, that's right. So that is xj, okay, and we are summing it up over all the j's, okay. So essentially what happens is that we have now, okay, if we are applying this w y0, delta y0 delta oi, okay, what do we get? Okay, we have to take the derivative of this, okay. So by taking this derivative, we can see that it becomes dou y0 dou WOI, that's given by dou WOI, okay, summation over j, okay, and there we will be having WOJ xj, okay, and what is it becoming? Xi. And what is Xi? That's the input. So now if I no, this is Xi only, right? So this if I say to be equation, okay, we should have marked the equations little earlier. So if I mark this thing as let's say equation 2, okay, 1 we have already marked. So if this is number 2 and if this one is number 3, then simply from this equation, if we look back into this, okay, it's possible for us to express this dou E dou WOI. So we have in that case dou E dou WOI to be equal to minus of T0 minus Y0 into Xi, okay. So this is what? This is nothing but the gradient, okay, and this is gradient with respect to one particular weight, okay, that is considering O as an output unit, considering I as the input unit, and we are able to find out the derivative of the error with respect to this WOI, okay. Now likewise we are having several O's, that's to say several output units and several input units which is indexed by I. So we have got several O's and several I's, okay, and likewise we will be able to find out the derivative. Now ultimately what is the direction in which we would like to move? We have found out the derivative with respect to this weight. Now as I told you that we have to move opposite to the direction of the derivative. So the correction that we have to apply to the Wij's, or the correction that we have to apply to the weights, okay, that is going to be what? That is going to be negative of this. That means to say, since this is already a negative quantity, okay, we have to consider minus of G, that is to say minus of dou E dou WOI, so that plus, with a positive sign we will be having T0 minus Y0 into Xi. Now the physical interpretation of this is quite easy, because what is T0? Target output. What is Y0? The actual output. What is Xi? Our input, right? So it's quite easy to interpret this, and all that it means is that the error term, that is T0 minus Y0, simply multiplied by the input quantity, and that is the correction that you have to apply, or rather you have to move in that direction. Now again the question that I had posed in the last class was that, now we have a surface like this, okay, a 3D surface, and this was our initial position, okay, and definitely by applying this kind of an algorithm necessarily means that we have to apply the gradient descent, okay. So gradient descent means it has to now slide down this surface, okay, and in that case, I mean, we could accelerate the sliding down, okay, we could retard the sliding down, okay, that, I mean, on that we can exercise some control, and control in what manner? If we, okay, this is the derivative that we have got, but ultimately what is the correction that we have to apply? Let us think of that, okay. Now this means to say that to this WOI, to the existing value of WOI, we have to apply a correction which we can write as delta WOI. And what that delta WOI is going to be? We can simply take T0 minus Y0 times Xi, isn't it? Meaning what? That if presently I have WOI as the weight, okay, then the new weight is going to be, the new synaptic weight is going to be the present synaptic weight WOI plus delta WOI, right? Can you see it now? So it is WOI new is going to be WOI old plus the correction that we are applying into it, right? So now I mean, there is a choice that either we can apply this correction in its entirety, or we can decide to multiply this correction factor by something, by some constant, okay. Let us call this as eta, okay. If we multiply this gradient by some constant quantity eta, that certainly does not affect our proceeding in the gradient descent direction. It is not affecting the direction. Only thing it is affecting is the rate at which we fall down, okay. The rate at which we fall down will be controlled by this parameter eta, all right. Now ultimately what we are doing out of it, okay, we are in some initial position and this is the minimum position which is our destiny. We are going to reach that, and through what process are we reaching? We are reaching that using a learning mechanism, okay. We are initially here, and then what did we do? We calculated that what error did we incur, okay, and based on the gradient of the error we are applying a correction, and correction in a correct way. I mean, correction in a manner that if from this position we come to this position, naturally the error that we are having is much less than the error that we were having out there. So we are reducing the error and slowly proceeding to the ultimate destiny. Now how fast we go is dependent upon this parameter eta, and since it is a process of learning, the best name that we can attach to this factor eta is the learning rate, okay. So here eta will be defined as the learning rate, okay. So if you are making the learning rate high, it learns faster. If you are making the learning rate slow, it learns slower. As simple as that. But think, is it as simple really? Because I mean, let us take the case of human learning, okay. A teacher can tell you that, you see, this neural network course, okay, has to be covered within 5 lectures, okay. I want to finish one semester neural network course in 5 lectures. So your learning rate has to be very, very high, and I am going to finish off 5 or 6 topics in every lecture. In 5 lectures the course will be over. If I tell you that, and if you start attending my lectures this way, okay, will you be able to learn that fast? You will have problems. So, ultimately what you will feel is that ultimately at the end of such 5 excessively high learning rate lectures, okay, you will finally conclude that no, I mean whatever we had learned, we have already started forgetting that. The teacher hasn't given enough of time to us for learning. Okay. Whereas if I go in the other direction, if I cover, I mean for every topic if I spend 3 or 4 lectures, okay, then ultimately at the end of 40 lectures you are going to feel that neural network is such a vast subject, but the teacher hasn't covered much of that. Okay, we were having very slow progress, but maybe by making slow progress, okay, you have come from here to here, okay, but okay, I mean you are not lost completely, but if you try to learn too fast, you may finally, I mean just go, I mean I may give you such a great push that you will cross the minima and ultimately you may fly away. That's possible. So, let us see that this learning rate that we are talking of is well optimal. Okay. We should not have the learning rate too high. Too high means it can lead to, essentially what it means is that it could lead to an instability or oscillatory behavior of the system. Let us say, I mean if we start conducting an experiment with alpha, I mean with this eta, what can happen is that if this eta is made too high, okay, it can come from here to here, it can come from here to here, and then it can go from here to here. It is remaining on the surface only, and then again it comes back from here to here, and the ultimate global minima position, it will be very difficult to reach. It will take more number of iterations, or in this case the behavior will be oscillatory in nature. Okay. So, that is not something that we are looking for. So, this learning rate is very important. In fact, the success of the neural network convergence, okay, a lot depends upon this learning rate. Okay. Let us understand that. So, having talked of this gradient descent, okay, essentially what we have done is that we have in this, I mean process, we have computed the I mean gradient of the error, okay, based on the linear neural network model. Why linear? Because this is essentially the equation that we have applied, the equation for the linear neuron, linear activation unit, that is what we took. Now, interpretation wise, what is this linear neural network leading us to? As I told you, a straight line fitting, a straight line fitting in n dimensions. That is what the problem is ultimately. But the question is that for any general data fitting, okay, or for any generalized curve fitting, okay, is it that straight line fitting is always the best solution? Never. For most of the practical data or practical situations that we encounter, we will be finding a nonlinear characteristics, isn't it? Let us consider a case that we have performed some experiment. Let us say y is equal to fx, that is what we are finding out, but we have y in this direction and x in this direction, and we have got the observations like this. Say these are the set of observations that we have got. Now, if I have to fit the best curve is certainly not the straight line. I mean I can attempt to fit straight line, but whatever attempt I make, okay, even the best attempt is going to give lot of errors. Okay. There will be lot of points which will be deviated from the straight line. So, ultimately what we have to fit through is some form of a curve. In this case, maybe that the best solution will be to fit a curve like this through all this set of points. If we could do that, that is the solution. So, we are ultimately looking at, I mean from a general point of view, we are looking at a nonlinear curve fitting problem. Okay. Now, there lies a problem, that if the problem is a nonlinear curve fitting, can we do it using the linear neural network model? Is the answer yes or no? No, because we cannot approximate okay, I mean there is a way whereby you can do it, that if it is a nonlinear function, you can break it up into piecewise linear components and then you could realize, but that's a very painful process whereby, I mean, you just break it up into piecewise linears and then try to realize all these straight lines using the neural network components. So that itself will be quite a complicated problem, in the sense that in that case you will have to fit several such straight lines with their individual slopes and intercepts. So many parameters you have to tune. Rather, if we could fit a curve like this, okay, then that would have been a simpler solution. So now what we have to look for, we cannot always have the linear neuron model, rather we should go in for some kind of a nonlinear model, right. Now, when such kind of problems cropped up, that ultimately a neural network has to approximate some kind of a function like this, okay, people started, I mean, researching with different types of neural networks, okay, or different models of activation, okay. And one of the activation models which people came up with, okay, is some activation function, if we could consider to be like this, that supposing this is the input, okay, supposing this is the input, let's call the input by x only, okay. Okay, I mean not the input, rather we should model it this way, that supposing we have got a neuron, okay, where we have got let's say inputs as x0, x1 up to xn, okay, and no matter whether we are using a linear neuron or a nonlinear neuron, this summer is essential, because ultimately what we are going to have is that after this summer we are following up this linear combiner with some activation function. Now, in the earlier case we had considered that to be simply a linear function only, but in this case this phi function that we are going to realize is going to be a nonlinear function. That is the only difference, but other things remain the same, meaning that if this is the neuron k which is under our consideration, then if this is wk0, wk1 and this is wkn, okay. So ultimately your vk, that is what you are getting as the linear combiner output, vk is equal to the summation of xj wkj, okay, and we are summing up for j is equal to 0 to n, okay. 0 to n means there we have included the bias as we had discussed in the model that we had followed in the last class. Now, here we have the vk, and it is the function phi of vk which we are thinking over, and ultimately we are having the output yk. Now, in earlier case we had got y, I mean we had made it, I mean for the linear neurons we had made yk equal to vk, but in this case we are just going to pass this vk through some nonlinear function yk, right. So, how are we going to do that? Okay. Let us think of some model, okay, where, so what is the input to this function? The input to this function, mind you, is vk, okay. So, the input is vk, okay, and the output is going to be yk, okay. So, this yk vk characteristics, okay, why don't we imagine like this, that let us consider a neuron whose response ultimately should lie in the range of 0 to 1. So, 0 to 1 is the ultimate range that we are talking of, meaning that when Vk, what is the range? Vk can assume, let us say, a value anywhere between minus infinity to plus infinity. Supposing that is the range that we are following for Vk, and in that range of Vk, Yk could have a value only in the range of 0 to 1, right. So, to get a characteristic like this, okay, we can say, okay, so that means to say that Yk's one value is 0, the other extreme is that it could take a value of 1, okay. So, we had that in the McCulloch and Pitts model, which we discussed in the last class, where we had followed a threshold logic. So, there in the McCulloch and Pitts model, we had considered that up to here the response was 0, here there was a discontinuity, and then it was equal to 1. But instead, if we think of a nonlinear function where the characteristic would be defined like this, that we do not exactly restrict Yk to binary values, but we consider that Yk could take values in the continuous domain, but within 0 to 1 range. So, in that case, why can't we imagine a function of this nature? We can imagine a function of this nature, okay, where we can say that when Vk is equal to 0, the value of Yk will be exactly midway between 0 and 1, that means to say 0.5 the value could be, okay, and we are going to realize a function of this nature, okay, where at minus infinity it will be Yk will be equal to 0, at plus infinity the value will be equal to 1, but in between it should follow a smooth slope like this. Now, mathematically we have to define this function, but let us look at some of the characteristics of this. Don't you find that this function that I have just now drawn, look at the characteristics of this function. First is that it is monotonically increasing. It is monotonically increasing function. And now, if I ask you to find out that is it continuously differentiable, it is. It is continuously differentiable. Mind you, McCulloch and Pitts function, which was a threshold logic, wasn't continuously differentiable, but this function is definitely continuously differentiable. Okay. So, this is having three characteristics: nonlinear, monotonically increasing, continuously differentiable. But I have drawn a shape like this. Now, you could tell me that no, I don't like your shape exactly. Okay. If you ask me to draw, I would have drawn it like this. Okay. Somebody can say that no, I should make it even steeper. Somebody can say that no, I want to make this function more flat. So, if I use this sort of a function as an activation function phi to this neuron, I should have some kind of a tunability. Tunability in the sense that I should be able to control the shape of this curve. And how am I controlling the shape of this curve? This is what I am doing, that either I am making it more and more steep. The ultimate of that is going to be McCulloch and Pitts model. Okay. If I make it excessively steep, it is ultimately going to approximate McCulloch and Pitts model, the threshold function. And if I go to the other extreme, then it is like a straight line. So, it is in between linear model and McCulloch and Pitts model where I can play around. Okay. And the function that we can think of in order to realize this, we can write it this way, that f of, or rather the phi function, phi of Vk, okay, we can write as 1 by 1 plus exponential to the power minus a Vk. Okay. If you plot the function, you will get some kind of a shape like this. In fact, The shape of this function is somewhat like this, isn't it? This is the kind of a shape, S-like shape. So that's why this category of functions are called as the sigmoid function. So these functions are quite popular. They are known as sigmoid function. So sigmoidal functions could be used as the activation functions for, as the nonlinear activation functions for the neurons. Okay. So this is just a realization of a sigmoidal function. It's not that sigmoidal function can be realized in only one way, but this is one way to realize this sigmoidal function. I think more of this, okay, we can see in the coming lecture. Okay. Any quick questions?